Okay, so my name is Sebastian, and I work for the R group in Boston. And we're busy implementing a neural network framework. So this talk will give a high-level overview of some things that, first of all, applications of neural networks and why they're interesting and why they're so hot currently. And then I'll give an overview of an actual case study of how we built ImageIdentify, so all the steps that are required to do something like that. And then at the end, we'll discuss quickly what's coming in either 10.4 or 11.0 for the new neural network framework. Okay, so the first thing is, what can you do with neural networks? And why are they so popular? So the most basic thing you can do is simple classification and regression. And we've already got that actually in the system, in classify and predict. And the thing we've got in classify and predict is the simplest type of neural network, where you have some inputs. So in this case, there's a three-dimensional input. So each of these nodes corresponds to one of the features. These features get connected up to a hidden layer, and there's some weights that tell it like how strong this connection should be, so for each of these guys. And the signal then gets propagated forward, and you have some output. In this case, there's two things. There's either true or false. So this is the most basic type of network. And these were already in existence in the 60s. And people were training them with backpropagation, which is basically just getting the derivative of the loss function with respect to all the weights. So this is a very ancient technology. But it works fairly well. Well, 60s, yeah. For me, it's an ancient technology. Okay, so that's a basic thing. Then there's specialist networks, however, for things like images. So for ImageIdentify, this is a basic example of this. The network looks something like this. Each of these points here is, so previously, these are actual neurons. However, you can abstract this to be a single layer, this whole thing. So when there's lots and lots of layers, you have something that looks like this. And the input comes in, and it gets fed through this whole network. And each of these modules here are different types of things that are specialized for images. The main operation is a convolution. And convolutions, they give the network all kinds of interesting properties, like, it gives it some translation invariance, for example, that you know images should have, et cetera, et cetera. So these are the very deep neural networks that are like 20 layers deep, or they go up to 30 to 40 layers. So this was in 2012, this was the big revolution that got sparked when neural networks came back into fashion. And that was for image recognition. And on this famous competition called ImageNet, you have like 1 million images that you can train on, and there's like 1,000 classes that you have to predict. And previous methods used all kinds of handcrafted features and then feeding them into support vector machines. And in 2012, neural networks just completely destroyed all the previous attempts at this competition. So this is a very basic use case that we've used a lot. And you can also have some fun with these networks. So this is something that I generated with ImageIdentify. And you can ask it basically, you can say what things, so you can say at this level, let's say, at this neuron here, what sort of images activate these neurons the most? So you can change the image gradually to activate the neurons the most. And it generally corresponds to things that it's seen the most of in training. So our training set for birds is extremely big. So whenever this thing starts seeing things, it sees a lot of buildings and it sees a lot of birds. Sure, yeah. So as you start with some image that is, it can be random image, it can be, in this case, just like some scene of some sky and some lawn, and then you let it go, and you say, how do you maximize the activations of some layer of this network? And then, you just change the image to make it more and more like that. Okay, so the second major class of networks, so these, for images and for just classification and regression in general, they're called feed-forward neural networks. And what that means is that the signal gets propagated continuously forward. We know, though, in the brain and for for other neural systems that there's feedback loops as well. So for things like sequence prediction, you have to have some sort of feedback loop. So you want to show it some character, then you want to have some state get passed back into the network, rerun to the next sequence of the character, et cetera, et cetera. So I've got a very simple example here, which we trained up So this is a very simple model. It predicts the next character in some sequence. So you can start it off with some initial sequence, and then it finds the conditional probabilities of the characters that come after this. And it does it again and again. So it finds the next character, then the next one, et cetera, et cetera. So in this case, we can try run this a bit. Let's see if this works. So I generated like 70 characters, and it started with, thou hast wrong. So it says, thou hast wronged thee, and I will take them to the gods to him. Okay, not completely perfect grammatically. But it's predicting, it has no concept of words in this case. It's just predicting the next characters. And you can also have longer sentences that you can generate from scratch.
This was trained on Shakespeare?
Yeah, so this is trained on some set of his works. You can also do things like code. So we train this on some amount of Wolfram Language code, and you can generate arbitrary amounts of what it thinks is correct code, which is usually, which breaks down at some point quite quickly. And you can start this off, whatever you want, or just randomly initialize it. Okay, that's a bit... These recurrent neural networks is that they take in some inputs, so like in this case it's a character, and they pass the state of the network to the next time step, and then you pass the next character in. And you have a single set of weights that you use for each time step. And that's very important. If you have too many weights, then learning can't happen really at all. Okay. So what becomes very interesting is when you start merging different types of networks. So here's one example. So there's been a lot of research on making image captioning work. And image captioning is actually very simple. So you just have a deep convolutional neural network, which is just feed forward. And the features, or the end of the network, gets fed into a recurrent neural network, which then has to start predicting words. And this is an actual output of Google's image captioner. So it has a picture of a market, and it produces multiple sentences describing what's in the market. It's not the sequences, so it takes in two things. So it takes in a feature for the image, so it takes in a single vector of numbers, and then it needs to predict, so when you're training this thing, you've got correct labels, or labels that humans have made. So it then needs to take that as a starting point and then generate a sentence. And there's some scoring function that you can use to see how good this sentence is compared to human-generated sentences. Okay, then there's been a lot of research now also on things like question answering. So, for example, there's a famous data set that Facebook has just released called Babi. And this is sort of an example of this. Like, John moved to the bedroom, Mary grabbed the football there, Sandra journeyed to the bedroom, Sandra went back to the hallway, Mary moved to the garden, Mary journeyed to the office, where's the football? And neural networks have gotten very good at this sort of question answering. And you can train them on just lots of data, and then on completely unseen textual logic problems, they do fairly well. And there's, Facebook developed a special kind of network that has some extra memory cells on it as well. But it's completely, it just fits into the normal network framework. And then obviously you can also then say, what about having a question answering system for images? So there's been a lot of recent activity for this. So you give it a picture, and it outputs you things like, you can ask it, what kind of store is it? Is the display case as full as it could be? Anyway, you can ask it any kinds of questions. And people are busy trying to build bigger and bigger data sets of questions that they've collected from the internet. So the biggest data set currently has like 15 million answers for questions on images. Anyway, so this is a very interesting application. And actually, we're building one of these things at the moment. Okay, these are just that's just a taste of things that you can do with neural networks. It's also, neural networks are the current state of the art on a whole bunch of other tasks. From speech recognition, we're busy building our own speech recognition system, to OCR, to video understanding, to a whole bunch of interesting, random things like counting the number of people in a crowd. All of these tasks are neural networks have basically no competitors for. Okay, except speech recognition. Actually, there's a. Okay, so I want to give a quick example of just how you actually go about building a system based on a neural network and a large scale, let's say, classifier. So in this case, ImageIdentify. So how do you go about something like this? So the first thing is you want to get almost all the visual categories in the world. So it's a huge task to get your own data sets for that, to build your own data set. So we started with ImageNet. So ImageNet is a very famous data set. I think Stanford is one of the groups that built it. And it was a semi-automated way of building this thing. So it had some curation in it, but mostly it was just scraped from the internet. It has 14 million images, like 20,000 categories. And the idea of ImageNet is that it's hierarchical. So you have right at the bottom of the hierarchy, you've got very specific things, and then you've got things higher up the hierarchy, like a bicycle is much more specific than a mountain bike. So we wanted to focus on predicting the leaves of this thing, so the bottom pieces, and then then get the probability of each of these guys, and then you can get the probabilities of all the higher things in the tree. Okay, so that seems very easy, simple, done. However, it turns out that this data set is of terrible quality. So some weird things, like they've got some bizarre categories of images. Things like Wandering Jew, and they've got a picture of Bob Dylan as an example of the Wandering Jew. And you can check this on the website for this link. So that's one set of things, like just bizarre categories that are not really visualizable and that you don't want in a system like this. And it'll be very embarrassing, like if for a user, instead of person, it returns something like this. So the second sort of piece that was annoying was certain categories were completely incorrect. So the scraping, so as an example of this, the shuttle. So the actual definition of the shuttle for this particular WordNet thing is a bobbin that passes the weft thread between the warp threads. So it's a sewing term. But all the pictures are basically pictures of space shuttles. So this is just two examples. The most common case, though, is just that there's many incorrect images in the classes. And especially for things that are very specific. So they've got very specific animal types as well, and bird types. And these, you can imagine, things go wrong there. So the question is, what do you do with this? Like, there's this huge mess of 20,000 of these synsets, of categories, and you have these 14 million images. You can't go through all the images. It's impossible. You're not going to get anything done. The curation will take too long for that. However, curation is still the solution, but you have to be clever about it. So the first thing, most basic step, is that you can curate what the good categories are for an image recognition system. The second thing then is you find what categories you're missing. So this was a thing this is a very hard thing to discover, that you're missing some category. So we did all kinds of things. Like I remember going around my house and getting my family to take photos of all the things that they can possibly see around their house, and try and get the recognizer to see these things, and then try and catch categories of things that we completely just weren't in this thing. Because certain categories of things, like weird things, like soap, for example, somehow there's no images in the soap category. And how do you catch that? Because your test set won't catch it very easily. Because your test set, there's nothing in there. But the most vexing one was certain categories were just completely polluted. Like something like 70% of the images were wrong. and sometimes grossly wrong. So the way to solve a problem like this that we found in the end was that you have a continuous feedback loop between the classifier and the curators. So the classifier, you train this thing up, and then you can see on the test set, what are we failing at? What categories is it confusing with other categories? And then those ones you send to the curators to say, is there a problem here? So we'd identify every day something like 200 categories of objects that we think that the classifier thinks might be getting confused with other things. So this went on for like 2 weeks or so, and we managed to clean up a lot of this stuff. And as soon as a category was bad, the curators would go in and just focus on that category, take out the bad images, and maybe find some extra images as well if there's too few of them. Okay, the second thing then is, another thing is, okay, so from this graph you should see now, one of the big challenges was speed. So this AlexNet, this was the state of the art circa 2012. This was Hinton's winning solution for ImageNet 2012. And it's fairly fast to train in modern terms. So the network we eventually settled on for training, which won last year's ImageNet competition, what's a variation of that one, that takes much longer to train than this. Roughly a factor, like it was a factor 8 or so slower. So if you have a CPU, so there's a framework called Caffe. These benchmarks come from there. So it's one of the most popular image classification frameworks. It has both GPU and CPU modes. And even on a very high-end CPU, 16-core Xeon, for this fairly simple network, it takes 43 days. And this was only for 1 million images. We were dealing with many more. So so we had a much slower network, and we had many more images than what you use for ImageNet competition. So CPU just completely was not in the question. So the only thing that you can really do is use GPUs. And we also had multiple GPUs. I'll show this now. So also, just for an interest, the GPU arms race just keeps on going faster and faster. And like next year, NVIDIA's promised us a factor 10 speed up over the current state of the art, using various tricks from 16-point precision for the neural networks. It's been seen that you don't need more than 16-bit floats, to a whole bunch of other memory acceleration and faster connection between different GPUs, etc. So there's more and more power coming very, very quickly. So so currently the best thing you can do, and which we bought for this project, was this sort of machine. It has 4 Titan X GPUs. Each of them has roughly 7 teraflop floating points power, and you can parallelize across 4 of these guys. So this is basically as much computing that you can get from a single power socket. So so then this is one thing. So also there was a whole bunch of things to get. So we were also constantly getting new data closer to the release, and we had to update the networks. So there was a bunch of tricks as well to prevent retraining the whole thing again and again. So you can fine-tune them. Otherwise, it would take far too long to retrain these things again and again. Okay, then there's a bunch of other things. So for a production system, you have to be very careful of, there's certain constraints that you want to have. So for a competition like ImageNet, all you care about is accuracy. But then as soon as you start caring about other things, like how long does it take to evaluate for the user, how big is it on disk? So one of the best networks last year on ImageNet was Oxford Group's network, and it's like 600 megabytes just to store the thing. And it takes something like 17 times longer to evaluate than our current implementation. So there's a whole bunch of compromises, and we found that a variation on GoogleNet was the best. It's very small, it has almost as good performance as this other one, and it's fairly fast to evaluate. And there's a whole bunch of other modifications that we played with to improve the performance of the original GoogleNet implementation. So tricks that came after this competition. Okay, so what's coming? So by 10.4 or 11.0, we expect to have some framework for training neural networks. It's designed to be used by our group for research and for other groups in the company. So it's designed to be extremely powerful and flexible and user tweakable. But it's also designed to be very, very easy to use. So we have a type inference system that Taliesin has made. That means that you don't have to give almost any parameters in the neural network. It will infer all the correct dimensions of all the layers, et cetera, if you don't want to. So even a very beginner can just string together a bunch of these layers, and it will know exactly. It won't throw you crazy error messages like other platforms like Caffe, et cetera. It will also obviously have GPU support because we want to use this internally for research. And our users want to have GPU support for this. And currently, yeah, it's by far the fastest thing to do if you have large data sets. So other things like that will add to our, so currently for machine learning, there's a few things we're lacking. So things like sequence prediction, we're lacking very badly in. So this framework will support recurrent neural networks, LSTMs, et cetera. And you can string these very easily together with convolutional networks that do things like the image caption generator, for example. So all the examples that I showed you, those are things that we aim to be able to implement very, very easily in the Wolfram language. And we will have obviously examples showing how to do that. Another thing that our machine learning framework doesn't currently have is any out-of-core learning. So for data sets that are bigger than, that fit into memory, like huge image data sets, this thing supports that for images and for a few other things. Then, okay, so eventually we also want to allow GPU training on the Wolfram language cloud. And this will make it very, very easy to do training. You don't have to set up your own GPU machine, and we'll obviously optimize it we can optimize it as much as possible for the exact GPU machines we've got in the cloud. And it'll be very easy to deploy the thing. It'll just be one of the easiest ways of training neural networks. And yeah, we're trying to keep, so currently there's a huge amount of research in neural networks, and there's just constantly innovations on different layer types that you can put into these networks to improve image classification performance or whatever else. And yeah, because we wanted this for research for ourselves, we obviously will implement the latest things that come out. So yeah, so that is what's coming hopefully in the next version.